So today I'm going to talk about probabilistic Kolmogorov complexity and some of its applications in average case complexity. My name's Haley, and this was joint work with Valentin Kabinets, Junjun Liu, and Igor Oliveira. So I'll start with a little bit of background on average case complexity. So you might accept the possibility that P could be different from NP in the worst case, but this wouldn't rule out a situation where for every language L in NP, every distribution D sampleable in polytime, there could be a polytime algorithm A that solves L well on average over D. So with all but negligible probability over D, A is correct about L. And here we're talking about so-called errorless heuristics. So A only fails by outputting a special failure symbol. It doesn't just sort of silently give the wrong answer. And this is what we mean when we say distributional NP is an average P, or NP is easy on average. So one of the ultimate goals of average case complexity would be to get a worst to average reduction for NP, basing the average case hardness of NP on its worst case hardness. This would rule out that sort of loophole where there do exist hard NP instances, but maybe one doesn't often come across them in practice. Or if you like, in the language of Impagliazzo's 5 worlds, this corresponds to ruling out heuristic. All right, so what progress has been made so far in this direction? Back in 1992, Ben David, Shore, Goldberg, and Luby showed that if you assume NP is easy on average, you get equality of NE and E. So that's a little bit weaker than we would like. The proof is very simple, just uses a padding argument. But using some more complicated ideas, there's an improvement in 2003 from Berman, Fortno, Pavin. So same assumption, and they show that you can actually find those NE witnesses in linear exponential time. So that's a non-trivial improvement. And then recently, last year, we get this exciting breakthrough result from Hirohara. He actually proves a number of worst to average reductions, but this is one of them. So in the assumption, we have to go slightly higher in the polynomial hierarchy. We assume sigma 2 is easy on average, but as a conclusion, we get worst case deterministic algorithms for NP with running time better than 2 to the n. It's also true here, as in the work of BFP, that you can actually find NP witnesses in that amount of time. And in this case, it'll be the lexicographically first witness. So I'll just note that the proof of this theorem relies heavily on some tools from meta complexity. Specifically this K superscript T, T time bounded Kolmogorov complexity. So I'll define this better later, but for now you can just think of it as the length of a shortest program that outputs X in time T. So at worst, this might be something like the string X itself, but in some cases, when X has some computational structure, you can do better. And then X is in some sense compressible. So inspired by Hirohara's work, we started thinking about this generalization to a randomized setting. So looking at a randomized errorless heuristic for sigma 2 in the assumption, and then trying to get worst case randomized algorithms for NP in the conclusion. So we were able to prove this, but before I explain how, I'll just talk a little bit about the motivation. So why would we want to answer this question? Well, for one thing, the theory of average case complexity is a little bit more robust when it's defined with respect to randomized algorithms. So say if NP is an average BPP just with respect to the uniform distribution, then the same is true for any polytime sampleable distribution. That's by Impagliazzo, Levin, 1990. Another reason is from cryptography. So if you view these worst average reductions just as like a stepping stone on the path to proving the existence of one-way functions from worst case hardness of NP, then this randomized setting is more relevant and is a necessary step because in crypto, of course, one tends to concern oneself with adversaries that might be randomized. So you might look at this statement and think it looks pretty similar to the deterministic version. You might expect it to go through without too much trouble, but I want to make the case that that isn't true. So it required some substantially new ideas, and this stems from the fact that Hiroharas reduction is non-black box. So to explain this, I'll talk a little bit about the framework behind Hiroharas proofs. So what I'm about to describe is something that's ultimately used in a few different ways in the course of proving the worst average reductions. But intuitively, you can think of this as sort of the main technical bridge between the average case assumption and the worst case conclusion. So we're looking at two distributions. The one on the right is just a uniform distribution, and the one on the left is something you can think of as a potentially pseudo-random distribution, although we are sort of playing to lose. But it's instantiated with a string y and a seed of uniform randomness. And then we apply this DPK construction, which, by the way, is a k-wise direct product of Hadamard codes. But we're thinking about what happens when there's an efficient, uniform distinguisher between these distributions. So I think it's fairly well known that proofs of pseudo-randomness are typically constructive, and that is true here. So I mean that we have this reconstruction procedure, which takes oracle access to a distinguisher. It's randomized, and in our case, it requires k bits of advice alpha, which is a function both of y and of the randomness r. And then with at least inverse polynomial probability, this procedure outputs that string y that we started with. All right, so how does Hirohara use this reconstruction statement? Well, he starts with an average case assumption, either NP or sigma 2 being an average P. He sets things up in a way that assumed errorless heuristic can be used as a distinguisher between those distributions. Now, it's also known that if distributional NP is an average P by Berman, Fortnow, and Pavan, then you have a PRG, which is sufficient to include BPP and P, and it's also sufficient to de-randomize this reconstruction procedure. So we de-randomize, R becomes fixed, and then alpha becomes fixed. So we have that there are some roughly k bits of advice, namely alpha, some log length seed to the PRG, and a few more bits to describe the rest of that uniform procedure, which is a program that outputs y. So just by definition, we have that kt of y is roughly at most k. Now let's take a look at what breaks under our weaker probabilistic average case assumption. So we still get a distinguisher D from our assumed errorless heuristic. D is randomized now, but that's okay. The problem is that we can no longer de-randomize via BFP. So looking at this reconstruction statement at the top, it's really not clear that there is any fixed, short, computational description of Y. So KT complexity really fundamentally doesn't work for us anymore. So what do? We end up introducing this so-called probabilistic time-bounded Kolmogorov complexity. So before I define this, I'll just give a little bit of background on Kolmogorov complexity in general. So classical Kolmogorov complexity asks, given a string x, what is the length of a minimal computational description of x? So intuitively, what's the optimal way for an entity to send a description D such that the receiver can eventually recover the string x from D? So by the way, the U up here denotes a universal Turing machine, and there's the option of conditioning on another string Z by including it on the input tape of U along with D. Okay, so K superscript T, time-bounded K complexity is similar, except now you would think of the receiver as a time-bounded machine. So the description D has to be such that X can be recovered from D in time T. Now, RKT, randomized KT complexity, is something that already existed in the literature. Now we're thinking of the receiver as a randomized machine. So D has to be such that with high probability, X can be recovered from D, which brings us to our definition of probabilistic KT complexity. So now we're thinking of the sender and receiver being in the presence of some shared randomness, and D is allowed to depend on that randomness. So what's the minimum length S such that with high probability over the randomness, there is some D of length S that allows a T-time bounded machine to recover X. So I think it's not too hard to see that PKT is at most RKT is at most KT. You may see an analogy with AM, MA, and NP. And it's also true here that de-randomization would make all three measures pretty much equivalent. All right, so how does PKT help us? Well, our approach now is just not to de-randomize at all. And then sort of already just by inspection of this reconstruction statement at the top, we have that PKT of Y is roughly at most K, because with high probability over R, there is some description of length K, namely alpha of Y and R, which yields Y. So I think this also explains why we couldn't just appeal to that RKT notion that already existed. The problem being that alpha depends on R. All right, so let's take a look at some of our worst to average reductions. So I'll note that these are all sort of probabilistic analogs of Hiroharas' main theorems. The first 2 points go through via sort of similar proofs once you have this PKT notion in place. With a couple extra tricks in part 2, you can get AM in the conclusion rather than just NP as you might expect. I'll just note that in number 3, for the randomized setting, we had to overcome some additional obstacles. They had to do with a sort of delicate inductive argument, and we ended up having to exploit not only PKT, but also RKT. And we saw this sort of interesting interplay between them, but I won't go into too much detail on that. So not only did PKT fulfill its intended purpose, but it actually ended up having some further utility. So one example is in learning. We get a strengthening of this result from Hirohara and Nanashima. So we get the same conclusion in the pack learning framework under our weaker probabilistic assumption. And the proof goes along similar lines, except it relies on the use of PKT rather than KT. And we're also able to get a probabilistic version of the fine-grained worst average reduction of Chen, Hirohara, and Vafa. So one thing I want to note about this is that a great deal of the technical work in that paper is in constructing a new efficient PRG for use in the fine-grained setting. So only incurring a quasi-polynomial overhead and running time. So this will certainly be of independent interest, but just to mention that our proof completely circumvents it because of course we don't de-randomize at all. Not only that, but our probabilistic worst to average reductions really do generalize their deterministic counterparts. So in particular, to obtain the theorem from Chen, Hirohara, and Vafa, one could just do things our way and then de-randomize via BFP at the very end. So here's a situation where the use of PKT yields a simpler proof even for the deterministic setting. So also just point to a couple further applications of PKT from Liu, Oliveira, and Zimond. And there's also some further discussion in this survey of Liu and Oliveira. So now I'll just go through a bit of a proof outline at a very high level. We'll focus on this simpler statement with NP in the conclusion rather than AN. So we're thinking of a language L in NP, considering an instance X, and if X belongs to L, then it has some lexicographically first witness Y sub X. So the goal is to show that with high probability, Y sub X is compressible given X. And we're looking at a time-bound tau, which is 2 to the n over log n, and we want to compress Y sub X down to length O of n over log n. Now, I claim that if we can prove this statement, it'll give us an algorithm to decide L. So what do? Given X, we guess some randomness R, and then we enumerate overall descriptions of length n over log n. We run each of these through our universal TM along with X and the randomness, and we see if any yields a witness. If so, we accept X. If not, we reject. And then just from the definition of PKT, that decision will be correct with high probability. And it's also clear that this isn't just an algorithm for deciding if X belongs to L. It's actually also an algorithm for finding a X first witness if there is one. All right, so here's a sort of one slide overview of the proof. This follows a simplified argument for the deterministic setting, which was given independently by these works at the bottom. The main ingredient in that argument is this symmetry of information statement for KT, which was also proved independently under the assumption that NP is an average P. So this all goes through for the randomized setting as well. In particular, we do get symmetry of information for PKT, provided distributional NP is an average BPP. I'll mention that the first two steps are proved via that sort of reconstruction lemma that I described earlier. So proving that some strings are PKT compressible. And the third step is proved via a simple hybrid argument along the same lines as in the original Hirohara 21. So looking at those first two statements, adjusting the time-bound t, we see that they have a term in common on the left-hand side. So we can put those two inequalities together and we end up with an upper bound on the pkt of y sub x. So this is a step toward our goal, but that upper bound takes the form of a so-called computational depth gap for pkt here. So that's where the third step comes in. And it says that for some time-bound t, if you let it be big enough, somewhere that gap has to be small. By the way, that's the only step that incurs that 2 to the O of n over log n running time in the conclusion. But it's not too hard to see, putting steps 1, 2, and 3 together, that we get the desired upper bound on the PKT complexity of a first witness. Okay, I'll just mention a couple of possible directions for future research. One goal would be to weaken the assumption of average case easiness that we start with. Now, I mentioned earlier that our argument requires the assumption of errorless heuristics. Now, ideally, it would be great to weaken this to heuristics that can fail in both directions by outputting 1 or 0. So the reason that I mention this is because there's this recent line of work from Liu and Pass and others that relates two-sided error heuristics for KT and the existence of one-way functions. So any connections we could get between this work and that work would surely be very interesting and fruitful, although I will admit that this may be a very hard problem. In particular, the sort of divide between errorless and two-sided error heuristics seems kind of surprisingly deep. And here are a couple of works investigating those issues. So another goal would just be to get matching time bounds in the conclusion. I think using our techniques, we can do as well as n time 2 to the n to the epsilon for constant epsilon smaller than 1 on the left-hand side, but that's about it. So in some sense, this just seems like the right conclusion to strive for, just an analogy with the BCGL. We can do it in the fine-grained setting, by the way. So those first 2 points apply equally well to deterministic KT complexity, but I think it would also be interesting to get any other applications of this PKT measure that we've introduced. Liu, Oliveira, and Zimond are able to get some results unconditionally using PKT, where arguments using KT only seem to work under some strong de-randomization assumptions. It's also true here that we're able to get some results without any assumption of de-randomization, although if you assume distributional NP is an average P, then you do happen to get de-randomization for free, but in other settings, who knows? But I do think PKT is quite a natural notion, this idea of compressibility in the presence of shared randomness, so I could certainly imagine it being useful elsewhere.